All right, let's jump right in. We're about to play detective and investigate a mystery that's hidden inside almost every sentence we read. We're going to uncover how computers first learned to solve one of language's biggest puzzles using a classic statistical tool, the hidden Markov model.
To see what I mean, just take a look at this sentence. Seems pretty straightforward, right? Time flies like an arrow. But for a computer, this simple sentence is a real head-scratcher. How many different grammatically correct ways could you actually read these 5 little words? You might be surprised.
And this is where the plot thickens. On the left, we've got the meaning we all instantly get. Time is a thing and it flies by super fast. But look at the right. There's a completely different, totally literal interpretation where time flies, as in a specific type of insect, actually enjoy an arrow. Both are technically possible. So how on earth is a computer supposed to know which one we mean? And that right there is the heart of our mystery. For a computer, figuring out the part of speech for each word is flies a verb or part of a noun is a classic detective problem. The words are the clues you can see, but the real grammatical meaning is hidden underneath. And to solve a case like this, you can't just throw a rigid rule book at it. Nope. You need a completely different kind of investigator, one that thinks in probabilities and what's most likely to be true. You need a probabilistic detective. So let me introduce you to our detective. The tool for this job is called the Hidden Markov Model, or HMM for short. It's a really clever statistical method that's perfect for modeling sequences and finding the most likely truth hiding just beneath the surface. An HMM works with 2 key types of information. First up, we've got the observations. Think of these as the clues we can actually see. The words themselves laid out right in front of us, like time, flies, like an arrow. But behind those obvious clues are the hidden states. This is the truth we're actually trying to dig up, the correct grammatical role or part of speech tag for every single word. Is flies a verb? Is like a preposition? That's the case our detective has to crack. Now, to make this whole thing solvable, our detective follows 2 simple but really powerful rules. The first is the Markov assumption. It basically says, to figure out the current tag, I only need to look at the tag that came right before it. The second is the output independence assumption. This one says a word like arrow only depends on its own tag, in this case, noun, and not on any other words or tags around it. Now, these are definitely simplifications, but they work surprisingly well. So, our detective has its rules, but how does it actually weigh all the evidence? Well, it all boils down to 2 fundamental types of probability that make up its entire toolkit. You can think of it like this. The HMM is constantly asking itself 2 questions. On the left, you have transition probability. That's just a fancy way of asking, how likely is a noun to show up right after an article like an? It's all about the flow from one tag to the next. Then, on the right, you have emission probability. This one asks, okay, if I know I'm looking at a noun tag, how likely is it that the actual word I see is arrow? This connects the hidden tag to the visible word. And this just makes so much sense intuitively, right? A phrase like the fox feels totally natural because the probability of a noun following a determiner is super high. But a phrase like the jumps just feels wrong. That's because the probability of a verb following a determiner is extremely low. The HMM is just putting numbers to that gut feeling we all have. Let's zoom in on a specific clue here, the word book. It has a really high probability of being a noun, as you can see from that first bar, but it has a decent medium probability of being a verb, like in book a flight. But an adjective? The chance is practically 0. Our HMN detective knows all these likelihoods simply because it's been trained by reading massive amounts of text. Okay, so our detective has its probabilities. It knows how tags tend to follow each other, and it knows which words are likely for each tag. Now comes the final act, sifting through all the possible combinations to find the one single most likely sequence of tags for the whole sentence. Now, just trying to calculate every single possible path would be a computational nightmare. especially for longer sentences. So the HMM has a secret weapon. It's an incredibly efficient method called the Viterbi algorithm. The real brilliance of the Viterbi algorithm is that it's smart, not just powerful. It doesn't check every single path. Instead, it moves word by word. At each step, it calculates the most likely way to get to that point and just throws away all the less likely options. It prunes the search space as it goes. So by the time it reaches the end of the sentence, it just has to trace its steps back along the winning path to reveal the single most probable answer. It's a really masterful piece of deduction. So after all that, how well does this classic detective actually perform? Remarkably well. Even with those simplifying rules, a well-trained HMM tagger can hit 90 to 95% accuracy. For a classic method, that is seriously impressive, and it's a real testament to how elegant the model is. So, in an age of these massive, complex neural networks, why do we even still talk about this method? Well, because the HMM story isn't just about the past. It teaches us a foundational lesson that is absolutely still relevant today. When you look at this case file, you can see the trade-offs really clearly. HMMs have a very narrow context window. They're basically only looking at the previous word. Modern models can see the whole sentence. HMMs are also a lot less flexible. But, and this is a big but, they need way less data to train, which can make them super valuable in certain situations. Of course, our detective isn't perfect. We know those simple rules can be, well, a little too simple for the real world. Language has all these complex long-range connections that an HMM just can't see. And that's exactly why more powerful neural methods were developed and are now king of the hill. And this quote really just says it all. At the end of the day, the hidden Markov model isn't just some dusty tool from the history books. It's a foundational concept. Understanding how this probabilistic detective works, how it models uncertainty to find the most likely path through a hidden world, is to understand a core piece of the logic behind language technology itself. It's the first chapter in a much larger story, which makes you wonder, what